My name is Xandra D'Arajo, and I am talking about some myths specific to mathematics education that we tend to perpetuate in various different ways. And so I just made these videos to kind of talk about those things and provide alternate ways of viewing some aspects about mathematics. If there are some myths that you want me to examine, just let me know. Okay, so this is the myth I want to counter today. So what I want you to do before we begin is to just think about, like, when people say math is black and white, what do they really mean? So in my experience, what it typically means is that math is math, it's objective, and that it always has a right answer, and there's not a lot of wiggle room or gray area. It's just math is math is math, and it's lovely in that it always has an answer. So this is a perspective that many of my students who tend to be pre-service teachers or in-service teachers come with. It's also a reason why many of us enjoyed math, because we were good at getting answers or doing procedures. And to say that math is not black and white actually is really hard to bring up with people who really enjoyed mathematics as being black and white or answer getting. And so I'm going to bring up some different perspectives in terms of, like, seeing math as not black and white in this short video. Okay, so this is kind of old now. It's like a year old, but I think it's still relevant. So from time to time, if you are on social media, and I imagine many of you are, you may have seen problems like this pop up. They tend to be centered on order of operations, and you can see this one up here. So this one circulated a year ago, and it raised a lot of commotion online, and it led to a lot of argument, which I actually think is great. I love to see people, general public, arguing about mathematics. But the reason why we saw posts like this and articles like this, like, can you solve it? And then we saw Twitter responses from people that say, I do it this way and I got 1. The answer is 100. I did it this way. According to PEMDAS, which we all know is like the word of law in order of operations, or is it? I got 1 as well. It's 16, OMG, the replies, embarrassing. So you can see it brings up a lot of ire, and it also brings up a lot of frustration because people are like, no, I learned it this way. It has to be this way. And people, when it doesn't come out that way, are like, but it has to have one answer. It's mathematics. It has to be black or white. It has to have a clear process and a clear answer. And in cases like this, we see often that it doesn't, typically because of notation choices and things like that. This is not the only area where it comes up. There's a lot of such problems in mathematics where there's dissenting opinions, so different opinions on what is the right answer. So we see in the top left, how many terms is that? Is it 4? Is it 2? Does it matter? Do we have to agree? So that's a question that we get a lot. In the middle, we say, there's a function. Is it quadratic or not? I've asked this question to roomfuls of teachers many times, and I've had 2 very different, strong opinions on the answer to that question. The bottom right, is it isosceles? I've been in conversations with classroom teachers who some of their textbooks say, yes, it is. Some say, no, it's not. So there is some wiggle room and black and white areas, or sorry, gray areas in terms of, like, mathematical conclusions, right? So I think part of it is because we use language to communicate. And so as we use language to communicate, that language gets communicated in various different ways. And so what I think is very interesting when these things come up, and there's multiple different ways, other people see as like the antithesis of mathematics, because mathematics should have just one clear answer. And I don't think that's the most interesting type of mathematics. So in the United States, at least, the Common Core State Standards had 8 mathematical practices for students to think about as they engage in math. And I actually think these are the more interesting parts of mathematics. Instead of just doing procedures, it's pretty interesting to reason, construct arguments, critiquing reasoning of others, modeling, etc. And these are actually parts of mathematics that aren't as black and white, because you can bring in a little more creativity and a little bit more of your own perspectives into these areas of mathematics typically. So this is where the interesting mathematics occurs to me. However, oftentimes when we're just thinking about mathematics as procedures or simple restating of facts, then it is kind of black and white most of the time. But I would argue, again, that it's not the most interesting math, but it is the most prevalent in K-12 schools, in high schools, and colleges probably too. So I'm just going to bring in this story of Dr. Miriam Erzakani, who I apologize if I mispronounce her name, but she was the first woman to win the Fields Medal, which is kind of described typically as the Nobel Prize in Mathematics. She did very interesting mathematical work that is far beyond where I went into my mathematical studies. However, she did unfortunately die in 2017. But in reading her obituary and what people wrote about her work, I found it fascinating to think about somebody who's devoted much of their life to the study of mathematics and reached the highest level of mathematics in terms of public recognition, in terms of how she described mathematics and how we often hear it described by our students. So one of the things that was written about her was that her work was deeply theoretical, but that it was also considered boldly original and of untold future importance. And so when we think about math being black and white and very clear cut, I don't think people that would describe work in this way would agree that black and whiteness of mathematics aligns one for one with work that is boldly original and of untold future importance. So if we're only doing work that's very clear cut, then we're not going to be able to see it as creative and original necessarily, because we're just replicating what has already been done. And this is why there's a greater emphasis on problem posing in a lot of math educators' work these days. She was also described as having fearless ambition, which again, I tend to not hear students and the general public or teachers even talking about ambition or fearless ambition in terms of mathematics. Typically, it's about speed and accuracy, which is not the way that I would think about mathematics in terms of like useful mathematics or also enjoyable or humane mathematics. So when I read her obituary, she also described her own work in these very interesting ways that I thought were worth highlighting. People recounted her talking about her process of sketching mathematical proofs, and she used really long white pieces of paper. There's a great article that shows her in front of one. And her daughter at the time referred to these as her paintings. So if you imagine mathematical work being displayed on these large pieces of paper being referred to as paintings by a child, and Dr. Mirzakani likened them to composing a novel. There are different characters, things evolve, etc. So if you think about this view of mathematics that's inherently creative and ambitious, it's very different from a perspective of mathematics as black and white and procedural focus. And I think we need to bring a bit more of this into our own teaching in classrooms. She also described her work saying she didn't have a particular recipe, but she developed a deep sense of joy from exploring mathematical problems. And this was one of my favorites. It's like being lost in a jungle, she said, and trying to use all the knowledge that you can gather to come up with some new tricks, and with some luck, you might find your way out. So if you think about somebody who's doing deep theoretical mathematical activity and describing their work in this way, most people wouldn't think of mathematicians' work as exploring or finding new tricks and getting your way out in this very animated, alive way of thinking about mathematics. But if you think about it, how awesome and how joyful would our classrooms be and our students be, and everyone's embracing of mathematics, if we did bring in some more of these aspects to our own work. So I'm not saying that we should abandon traditional mathematics. There is a time and place for fact fluency. I don't think it needs to be the bulk of every grade level of every content, but I do think there is a place for it. But I'm just going to explore how we might expand on the notion of 14 times 25 to really get at a little more creative ways of doing some pretty procedural and what some would call black and white mathematics. So you could do 14 times 25. That's pretty typical. It's in a lot of textbooks. But you could also ask students or people, could you find factors whose product is 350? So if your goal is just to practice with multiplication facts, then this still is getting in that practice and still getting at the idea of multiplication, but you're reversing the problem so that you're finding two products whose two factors whose product is 350. That allows for a lot more creativity. Actually, I said two, but that doesn't say two. So they could find 5, 10, 15 product or factors whose product is 350, et cetera. So it really opens up for a little bit more of the exploration and finding new tricks and tips for doing this. You could also bring in some of the mathematical practices that I brought up earlier. So you could say something like, Jill thinks 14 times 25 is the same as 13 times 26. Seems kind of logical, right? Because you're just making one smaller and one bigger, so it should work, right? And then you could say, do you agree or not, and why? So now we're getting, again, we're getting deeper into the mathematical ideas. So it's not black and white, although there is a correct answer, but the way that you can explain and engage with this problem is actually quite fun, and it allows for lots of avenues. 14 times 25 is the same as 28 times what? Explain. So again, maybe there's one right answer, right? However, there's so many different ways to arrive at it and so many different ways to explain it that it makes it a lot more fun, interesting, and it allows for more of this creative energy and ambition to come out of our students. Jose says 14 times 25 is the same as 7 times 50. Do you agree? Explain. So kind of the same idea as the prior one. So you can kind of see that when we do problems like this and really expand how we're getting at some of these basic ideas, students might start to think about mathematics as more than just black and white. They might start to see it as a creative and joyful endeavor to some extent. And then finally, some of my favorite ones are tell me a story problem that could be modeled by this. So really letting the creativity come out where you do get to pick the characters that you're modeling in this story. So that's it for this video. I hope you enjoyed thinking about what does it mean for math to be black and white? Why do people say that? And what are some different ways of perceiving mathematics? Stay tuned. I'll have the next video in this series up in a week or so. Take care.